Hello. So today we're going to talk a little bit about rudimentary equations used in advanced propulsion theory, particularly in relation to reaction engines. So we can imagine we've got some kind of engine nozzle which is at the back of a spacecraft, and we are ejecting material. This might be plasma, some material that carries energy, kinetic energy, that is responsible for the thrust generation for the reaction engine, and we define the velocity of this exhaust stream as being the exhaust velocity because it's the velocity of the material in the exhaust. The mass flow rate is the amount of material, such as the fuel, in a given burn time, which can also be equated to, say, the capsule mass for a nuclear pulse detonation system multiplied by its pulse frequency, and this is in the units of kilograms per second. And then the thrust is simply the mass flow rate times the exhaust velocity, which might be in kilonewtons or meganewtons. The jet power is 1/2 of the exhaust velocity times the thrust, or 1/2 of the exhaust velocity squared times the mass flow rate, which might be in the units of megawatts or kilowatts. And the specific power is simply the jet power divided by the propulsion mass, and that will be in the units of kilowatts per kilogram or megawatts per kilogram, often called alpha in the literature, often given in inverse units of kilograms per kilowatt, for example. And what defines the propulsion mass is the mass of the engine, the mass of the power supply, the mass of the lasers in this case, and the mass of the heat management radiator system. But it might have some power system, which is what starts the whole system up. It might have, some shielding here, and then we might have some laser system, which is what's responsible for detonation of the pellet materials, and a bit more structure. And then the engine nozzle, where the material is ejected to give us thrust. And then, because the system gets hot, it may need some radiators. And this gets rid of the excess heat which is generated from radiation impinging on the material structure. So this helps to keep the spacecraft cool, and these are essential, and you often see those on advanced spacecraft designs. And so all of this, the radiators, the engine nozzle, laser system, power system, will be included in the specific power calculation, which is the jet power over the mass of the propulsion system. But it would not include the structure or the payload. That would not be included in this calculation. And finally, just to talk a little bit about the meaning of the jet power and why it's important. So we can actually define the energy output of a reaction engine system as being equal to alpha, which is the mass defect, times the burnout fraction, times the mass of, say, a capsule of fuel, times the speed of light squared. And if we multiply that by the pulse frequency of detonation, we get a power output. So power out, which is equal to alpha phi n cap F hertz c squared. And remember, the jet power was equal to 1/2 m dot v exhaust squared, and it can be shown that the exhaust velocity is approximately equal to 2 alpha phi to the power of 1/2 times by the speed of light. And so you can actually take the ratio of the jet power and the output power, and the ratio of these two terms, P jet over P out, which is 1/2 m dot Vx squared divided by alpha phi m cap f hertz c squared. This is actually equal to the jet efficiency. So that is what the jet efficiency is the ratio of the jet power over the output power. And as you can see, if we actually substitute for the exhaust velocity in the numerator, all of the terms will cancel and this will be unitless. So let's just do that quickly. So let's get 1/2 m dot, and it's Vx squared, and that's square root 2 alpha phi. So 2 alpha phi, the square goes, and we've got c squared divided by alpha phi m cap f hertz c squared. And we can see that the c squared terms cancel, and we can see that we've got 2.5 here, so they cancel, alphas go, phi's go, and we're left with m dot divided by m cap f hertz, but of course m dot is just m cap f hertz, so they cancel as well. And so m cap f hertz over m cap f hertz, and so is equal to 1, so we have no units. So it's important to understand this is the meaning of the jet efficiency. It is defining the ratio of the jet power over the output power of your system. So it's a measure of how efficient your engine is, how efficient that it is at converting the power inside the engine, the output power that's generated from the reactions, into the jet that comes out of the exhaust. And so just to illustrate, here's some numbers which are made up, so don't take these too seriously. But let's say we had an exhaust velocity of 100 kilometers per second, a mass flow rate of 10 kilograms per second. This would result in a thrust of 10 to the power of 6 newtons, 1 meganewton. Jet power will be 1/2 times 100 times 10 to the 3 meters per second times 1 times 10 to the 6 newtons, which gives us 50 gigawatts of power. And let's say we had a propulsion mass defined by an engine mass of 100 tons, an ignition laser system 20 tons, a power system mass 50 tons, radiators and coolant 30 tons. That would give us a total propulsion mass of around 200 tons. And so the specific power will be 50 times 10 to the 9 watts divided by 200 times 10 to the 3 kilograms, which is 0.25 megawatts per kilogram. So it just illustrates simple calculations in advanced propulsion theory, particularly in relation to reaction engines. That's it.